This talk describes our observations of stellar flares on the star AD Leo using time series spectroscopy. The team was Al Stiewing in Phoenix, Arizona, Jack Martin near London, England, Woody Sims in Gilbert, Arizona, and yours truly in Gold Canyon, Arizona. We used amateur scale telescopes and commercial spectrographs. Al and Jack used Sheliak L high res, Woody used a Sheliak Lisa, and I used a Sheliak Alpi. You're all familiar with solar flares powered by magnetic activity on the sun. Not surprisingly, other stars display similar flares. They're easiest to detect on dwarf M stars. Because the star is relatively faint, the flare can present a large relative signal. AD Leo is one such flare star known to be particularly active that has been the subject of quite a few papers describing flares that were observed by both photometry and spectroscopy. We monitored AD Leo to address two questions. First, could we see anything at all that represented stellar flare events? And second, if we did see something, might our observations be of some use to this field of research? As it worked out, we did indeed see clear signatures of stellar flares. The scientific value of small telescope spectroscopy of these flares is still a bit of an open question, but the prospect is tantalizing. Here's an example of what happens during a flare. The plot is intensity versus wavelength, zoomed in on the H gamma line. During quiescence, this line is in emission. As the flare begins, the emission flux rises and then falls. The entire sequence took about an hour. If you calculate the equivalent width of H gamma and the other Balmer lines versus time, you get this group of curves. Another way to display the evolution of this event. Note the rapid rise in equivalent width followed by a gradual fall back to quiescent level. In a moment, I'm going to show an animation of this flare. The Alpi spectrum covers the wavelength range 3,900 to about 5,000 angstroms. The animation shows 13 spectra, each representing a single 5-minute exposure. The images were taken continuously, so this is 1 hour in the life of the star. I'll play it twice. In this first run, watch the H gamma line near the center of the spectrum. Note how H gamma strengthens quite rapidly and then fades more slowly. I'll play this animation again. This time, watch H beta on the far right and H delta left of center. The Balmer lines rise and fall in sync together. There's a hint that calcium K may be responding somewhat differently, but the signal to noise ratio is pretty low at the blue end, so we're not yet sure of the significance, whether that's real or not. The rest of the flare event certainly looks real, but we want to put that into a firmer foundation. To do that, we followed two paths. The first was a statistical evaluation of the data. We examined the time variation at each wavelength in the continuum region outside the emission line and determined the standard deviations, a noise level. Then we asked if the change in flux within the emission line is statistically significant at the 3 sigma level. Here, the increase in flux in the emission line is about 20 times the continuum noise level. That sounds pretty real. In our graphs of equivalent width versus time, we use the continuum signal to noise ratio to calculate error bars on equivalent width. As shown in these Lisa spectra, R about 1,000, the flare signature is definitely larger than the error bars on all the Balmer lines. So again, we conclude that this is real. We also note some qualitative indicators. You've seen how the Balmer lines all increase and decrease in sync with each other during a flare. It's hard to imagine how a noise or an artifact could cause that. A few events were seen simultaneously at 2 observatories. Here's an example. Woody and I are separated by about 20 miles as the crow flies. We use different telescopes and different spectrographs. We both saw this event at the same time to better than 1 exposure duration, and our observations give almost identical plots of equivalent width versus time for all the Balmer lines. There were a few more flares observed at both observatories, and there was never a situation where 2 observatories were monitoring at the same time and one of them failed to see a flare that had been detected at the other. So we have both negative and positive independent confirmations that these events are not local artifacts. That's comforting if you remember the story of the microwave oven at a radio observatory a few years ago. In all respects, our observations are consistent with what professional researchers have seen. The rise and fall of emission line flux is very similar. The sharp rise in equivalent width, followed by a gradual return to the quiescent level, and the typical 1-hour timescale are also consistent with what professional researchers see. The professional researchers sometimes watch all night and see pretty much nothing. We had nights like that too. Not all flares show the stereotypical impulse and fade kind of a profile. Sometimes, for example, as shown on the right here, a second flare starts before its predecessor has fully faded away. We saw similar events and events where the rise was much more gradual than the stereotypical impulse profile. Up to now, I've been showing low resolution LISA and ALPI spectra. We're interested in the potential for high resolution spectra because some research papers have reported various types of line profile changes during flare events. For example, one distinction between a flare versus a coronal mass ejection is the ejection speed, which will presumably cause a blue shift in the line. As far as I can tell, no unambiguous coronal mass ejection has ever been reported on AD Leo. Researchers have reported line profile changes during a flare, particularly enhanced wings in the emission lines. That leads to little or no change in the full width half maximum, but a noticeable increase in full width at 10% flux, for example. Seeing these is obviously a real challenge for small telescope spectroscopy. We've done experiments that give us hope, such as these H beta line spectra, R of 6,000, exposure 10 minutes, no flare during this experiment, but the noise does not seem to be excessive and the line profiles are consistent. Also, look at these H alpha spectra at an R of 16,500, also 10-minute exposures. On this night, we had both L high-res and LISA spectra on the target at the same time, and the two instruments saw the same signature in terms of flux change and equivalent width change for a small flare event. So, back to our starting questions. First, can we see anything that looks like a flare? Yes, absolutely. We are definitely seeing real activity on the star. In 188 hours of observing over 27 nights, we recorded 31 statistically significant flare events. That's one flare per 6.1 hours, which is consistent with other reports for this star. One researcher in the field who saw our initial results said, "I'm very happy you successfully got flares." The second question was, can small telescope spectroscopic observations have value to this field of research? That same researcher thinks yes. Our ability to make long observing runs, devote many nights to the target, cover the entire optical band with low resolution spectra does bring something to the party. That should puff us up enough to keep us going for a while, I think. We have three lists of next step action items. First, we have a collection of high resolution H beta spectra that we need to analyze. Second, there are additional analyses that should be applied to our current data set to search for time lags between various spectral lines, line profile changes during the flares, and revisit the trade-off between sensitivity versus time resolution. Third, we plan follow-up projects, including aiming at one or two more flare stars, finding a few more collaborators, finding a mentor, and arranging for simultaneous photometric monitoring to accompany these time series spectra. This is still an exploratory project, but it looks like we're on to something. Thank you for your interest and your attention.